All right, ladies and gentlemen, let's get started on 8.2. We are going to learn a new method, and this is our last new thing for Calc. Woohoo! We're going to do integration by parts. So our objectives are that we're going to use integration by parts to help us find antiderivatives. This method is particularly useful for integrals involving products of algebraic and transcendental functions. So for example, if I had an integral that looked like x natural log of x dx, I might want to use my integration by parts. Or I could have one that looked like x squared e to the x dx, because if I try my u substitution, that's not going to be too helpful. Or it might look like something like e to the x sine of x dx. It's like, well, that's kind of yucky. So here's what we're going to do. We're going to talk about integration by parts. So I'm going to kind of show you how this was developed, just a wee bitty case of it, because I think it's helpful. If I took a derivative of u times v with respect to x, then it would be u times dv dx plus v times du dx, okay? And this is the product rule, right? So this is u v prime plus v u prime. And that's our product rule. So if both pieces are continuous, then I can integrate both pieces, alrighty? So then I could say, so if I integrate this, remember that I would get back u v is going to equal the integral of u v prime dx plus the integral of v u prime dx, okay? And then when I do, I could also rewrite this as uv is equal to the integral of u dv plus the integral of v du, okay? So basically I just keep rewriting things. So that's what integration by parts is. So integration by parts, and this is the key piece right here, is my integral of u dv is going to equal u times v minus the integral of v du. Alrighty, and that's the formula that we're going to use. So now let me give you some guidelines. Oops, I spelled it wrong. It's helpful if you spell your guidelines correctly for our integration by parts. Okay, so the first one is you want to try to let dv equal the most complicated portion of the integral, okay, and that you want it to be something that you can manage, so it's going to fit a basic integration rule. Then u would equal all the stuff that's left over, remaining stuff. So technical, all right? That doesn't work. And remember, sometimes just like with u substitution, you have to try things a couple of times to make sure that it works. We're going to let u be the portion of the integrand, whose derivative, and I'm going to do lots of examples for us today, whose derivative is simpler than u, then dv is everything else. So it's going to be your remaining stuff. The thing that is important is we always want, and I'll put a star by it, the thing that's important is dv is always going to contain, always includes the dx of the original integrand. All right, so we're just going to do some of these by trial and error and work through a bunch of examples, and then it will get better. Okay, sometimes these problems are a little bit entertaining, but I think you guys will be okay. So here's our first example. We're going to find the integral of x e to the x dx. So let's just say we attempted our normal u substitution. So if I let u equal e to the x, then du is e to the x dx. Well, that wasn't too helpful. But what if I rewrote my integral, and I'm going to make it a little bit bigger so I can delineate some of the pieces. What if I let this guy be u, then this be dv? Alrighty? Okay, so let's just start here. And there's a lot of other ways you could break everything up, but we're going to just start here. Alright, so I'm going to let u equal x, then du is equal to dx, okay? And then my dv is going to equal e to the x dx, but I need to get to my v, so I'm going to integrate e to the x dx, because if I start with the derivative and I integrate it, I get back to v, because I'm going backwards. Then v is going to equal e to the x, okay? Alright, so I need this information and this information. My formula for integration by parts is going to be the integral of u dv minus the integral of v du. So now I just have a lot of substitution to do, and if you write all of this stuff out, it makes life so much easier. So now let's, oh, I wrote it down wrong. My bad. Whew, I was thinking, what the heck? Equals u times v minus the integral of v du. Whew, I forgot a piece. There we go. So now this is our original integral, and this is where we're going. And notice I have a product. So let's substitute everything in we know. So I'm going to say my original integral is equal to u, which is x, times v, which is e to the x, minus the integral of v, which is e to the x du. And my du is my dx. And again, I'm just substituting in everything that I have. Now I need to simplify, so I'm going to have x e to the x. The integral of this is e to the x plus c. And we're done. Woohoo! All right, because we don't have a product rule for integration, so I have to do a different type of work. So I'm kind of doing a product rule for integration, but this is our rule, and I'm going to write this every time to make sure that we can kind of learn that. Alrighty, so let's do another example. And sometimes you might pick the wrong thing for u and dv, but if you do, then we just try another method, just like when we did u substitution. So I'm going to do x squared natural log x dx. Alright, so the complicated, I'm going to let u equal that part. So u is equal to the natural log of x. So then du is going to equal 1 over x dx. Well then if u is equal to this, then dv is equal to everything else, x squared dx. Then v is equal to the integral of x squared dx, which is x to the third over 3, and then I'm going to have a c when I'm done. Okay? So now if I do my integration by parts, which says that the integral of u dv is uv minus v du, my u is the natural log of x, my v is x cubed over 3. I'll bring the c in a little bit. And then minus the integral of minus v, so v is x to the third over 3, du is this guy 1 over x dx, okay? So I do have to do this, but I'm going to rearrange this and pull this guy out front because it's polite, natural log of x, and then I have x goes into that x squared, pull the 1/3 out front, integral of x squared dx, right? So this is going to equal x cubed over 3 natural log x minus 1/3 x cubed over 3 plus c. You have to have that c in there. Fix this a little bit, and I have x to the third over 3 natural log of x minus x to the third over 9 plus c. Woohoo! And we're done. Now technically you could factor out an x cubed over 3, but remember at some point it becomes a little bit silly, so I think you could just stop there. All right. Next example. This one says evaluate, which means we have a little bit of math to do, and we're going to integrate from 0 to 1 the arc sine of x dx. All right, so, oops, you can't see it, sorry. So in this one, we're going to let u equal the arc sine of x dx, okay? So du is going to equal 1 over 1 minus x squared dx, okay? So if u is equal to my bad. That guy goes away, sorry. So u is my arc sine of x. I know this is a little bit weird, but my dv is going to equal everything else, which is dx. So my v is the integral of dx, which is going to equal x. So now I have my u, my v, du, dv. So my integration by parts is the integral of u dv is u times v minus the integral of v du. So I'm going to substitute in my u, arc sine of x, times v, which is x, minus the integral of v, x, du, is 1 minus x squared dx, okay? Well, this guy, so I'm doing a different u substitution now. I'm going to manage this integral. So this one I'm going to let u equal 1 minus x squared, so du is a negative 2x dx. So notice in this one I need to introduce my half. So this becomes x arc sine of x minus 1/2 integral of 1 over the square root of u du. And I'm just going to rewrite this as u to the negative 1/2 du. So then this becomes x arc sine of x minus 1/2, and then I have u to the positive 1/2, and then I'm going to squeeze my 2 over 1 in there. There's my c, okay? Those two guys cancel. Substitute my u, arc sine of x minus u, where'd u go? It's right here. My 1 minus x squared to the 1/2 minus 1 minus x squared plus c. So I did have a lot of u's in there, but you do need to be careful. And my bad, we're going to integrate this from 0 to 1. So we're not quite done, just kidding. So this is going to be 1 arc sine of 1 minus the square root of 1 minus 1. So that guy goes away. Okay, minus 0, that term goes away, minus the square root of 1, because 1 minus 0 squared is 1. So this is 1. Sine is 1 at pi over 2. Okay, and then that guy went away because the square root of 0 is 0, plus the square root of 1 is 1. So now we're done. Whew. All right, so sometimes when we do integration by parts, we have to do it multiple times. And so that's what our next example is. Okay, and I think, let me just check, we only have 2 more examples, so that's not so bad. So let's find the integral of x squared sine of x dx. So when we start, I'm going to let u equal x squared, so du is 2x dx. So if u is equal to x squared, then that means that dv is the sine of x dx. So v is going to equal the integral of the sine of x dx, which is a negative cosine of x plus c. All right? So if I do my by parts, which says that the integral of u dv is u times v minus v du, substitute all my stuff in, I'm going to get u, x squared, times v, negative cosine of x, minus the integral of v, a negative cosine of x du, 2x dx. Okay? All right. And eventually I'll get a c in there, but I'm not going to do it quite just yet. So this one is a negative x squared cosine of x negative, negative. This is a plus integral of 2x cosine of x dx. Well, if you notice, we have another integration by parts, okay? So now we're going to do it again. So this time I'm going to let u equal 2x, du is 2 dx, so that means that dv is the cosine of x dx, so v is the integral of the cosine of x dx, okay? Whew. And this is the sine of x, technically, plus c. I didn't put my c in there because I'm still working, so I'm gonna get another c when I'm done. So I'll put my c in when I'm done. So technically there's a c there, but I'm gonna keep going, okay? All right, so now if I do my by parts, and I know you don't have to write this, I'm just trying to help us get this stuck in our head. So it's uv minus the integral of v du. So my u, I'm going to write this guy down so I don't lose him in the process. So I have a negative x squared cosine of x, okay, plus my u, which is 2x, and my v, which is the sine of x, minus the integral of the sine of x du is 2 dx, okay? Now we're getting somewhere, okay? So if I do my math, this is a negative x squared cosine of x. This guy is 2x sine of x. Pull that 2 out front, sine of x dx. Now that guy's pretty easy, right? Whew, hopefully my last time to rewrite. Negative x squared cosine of x plus 2x sine of x minus 2, and then the derivative, or sorry, the integral of sine is a negative cosine, so plus the cosine of x. Now I have a c, and there's my answer. Holy cow. So you have to keep going with your integration by parts until you run out of stuff to do. All right, last example. This one says find the integral of secant cubed x dx, okay? So on this one, I'm going to let u equal secant of x. So my du is going to be the secant of x tangent of x dx. So then that means that dv is secant squared x dx. V is the integral of secant squared x dx, which is the tangent of x plus c. Okay, so this is where your memory work really becomes helpful. So then my integral of secant cubed x dx, and I'll write my parts up here. So the integral of u dv is uv minus v, oops, where did I write that? The integral of v du. There we go. Sometimes I get a little slap happy with where stuff goes. All right, so I have u times v. U is the secant of x. V is the tangent of x minus the integral of the tangent of x times du, which is secant x tangent x dx. Okay, so then I'm going to clean this guy up a little bit. So here's my secant x tangent x minus the integral of secant x tangent squared x dx. I don't have an integral for tangent squared, but I do if I rewrite it. So I'm going to rewrite it again. Tangent x minus, so here's my secant x. Tangent is secant squared x minus 1 dx, yay Pythagorean identities. I'm going to fix this mess. So here is the secant of x, tangent of x minus the secant cubed x minus the secant of x dx. Okay, I'm going to split this guy. This is all in parentheses, by the way. I'm going to split that integral up. Here's the secant of x, tangent of x minus the integral of secant cubed x minus the integral minus plus the integral of secant of x dx, because a minus and a minus is a plus. All right, so This one, I'm actually going to show you this. This one's kind of cool. Here's secant cubed x dx. Well, I have a secant cubed x dx over here, and I forgot my dx right there. So I'm going to take this guy over here. So I'm going to get 2 secant cubed x dx is equal to the secant of x tangent of x plus the integral of the secant of x dx. Well, the integral, this guy becomes the natural log of the secant of x plus the tangent of x plus c, divide by 2, woohoo! So I get secant cubed x dx is 1/2 times the secant of x tangent of x plus the natural log secant x plus tangent x, whew, plus close bracket c. Ta-da! That one was pretty unique. So, whew, that one's done. All right, so the moral of the story is you have to be patient, and sometimes you might have to choose your u and your dv a couple of times until you get better at the process. All right, good luck rereading back through these, and I will see you tomorrow.